Modern autonomous vehicles are complex cyber-physical systems, massive computer networks on wheels that must constantly translate digital code into physical action. To reach the road, these machines must satisfy two distinct regulatory masters: functional safety and cybersecurity. These two disciplines have opposing needs. Functional safety relies on speed. If a pedestrian steps into the road, the car needs low-latency, immediate reactions to halt. Cybersecurity, however, requires the intentional friction of heavy encryption and data validation to ensure the car's signals haven't been tampered with. This creates a paradox. Optimizing for safety can leave the car's network open to hackers, but optimizing for security adds processing delays that can make the car too slow to avoid a physical obstacle. In many traditional automotive workflows, the safety and security teams work in isolated silos, rarely sharing a common data environment. Security teams often track their threat analysis and risk assessment, or TARA, in static, disconnected spreadsheets. Because these text documents cannot mathematically interact with physical design files, contradictions remain hidden. Engineering teams often fail to spot fatal design flaws until they build and test physical prototypes on a track. Flat documents lack the structure to manage the multidimensional complexity of a modern vehicle. Relying on them leads to architectural blind spots and the massive financial waste of late-stage redesigns. Industry is shifting toward model-based systems engineering, or MBSE. At the center of this is SysML v2, a language that replaces disconnected spreadsheets with a unified mathematical architecture. SysML v2 allows engineers to define cybersecurity threat models using textual notation. The system then instantly generates the corresponding visual blueprints, keeping the logic and the layout synchronized. This allows us to trace a specific security goal directly down through the architectural layers to the individual software components. Using the allocate function, this software logic is mathematically tied to a specific physical microchip, like a hardware security module. This mapping creates a true digital thread. If an engineer changes a microscopic hardware spec, the macroscopic regulatory models update automatically, ensuring that design stays consistent. To see how this prevents failure, consider a vehicle that encounters an obstacle and must trigger its emergency braking. The functional safety requirement is rigid. The vehicle must detect the obstacle and halt within 100 milliseconds. Now we add the cybersecurity requirement. To ensure the stop signal isn't a hacker spoof, the over-the-air receiver mandates 50 milliseconds of encryption validation. Finally, we add the baseline system limits: 30 milliseconds of network latency plus 40 milliseconds of mechanical processing time. The total reaction time now hits 120 milliseconds. The math here reveals a serious crisis. By enforcing the new security rule, the car will now fail to stop in time, leading to a physical crash. SysML v2 catches this during the design phase. The moment the 50 millisecond requirement is entered, the system's Assert constraint flags the timeline overlap and blocks the design. By acting as a mathematical referee, the language forces engineers to resolve the trade-off, perhaps by upgrading the processor, long before physical manufacturing begins. Engineering has evolved into a software-like discipline, where blueprints are no longer just drawn, but compiled using a system-as-code philosophy. This allows manufacturing teams to adopt agile DevOps pipelines. Teams use version control systems like Git to track and merge changes to physical car parts. Every time an engineer satisfies a design constraint, the toolchain logs a cryptographic signature. This hashes the model snapshot and the expert's approval into an unchangeable record. This creates a signed evidence chain. Regulators use this mathematical audit trail to verify that every safety and security requirement was met by the design before the car ever hits the assembly line. In a world of connected automation, the boundary between digital security and physical safety has vanished. Protecting human life requires an engineering language built to mathematically resolve paradoxes, rather than just documenting them in a file. SysML v2 moves the industry away from reacting to flaws. It allows us to actively compile a future that is truly secure by design.